Okay, thank you very much for having me. I work in the developer technology team in NVIDIA. Similar to Paul, I used to work at EPCC, the Parallel Computing Centre at the University of Edinburgh, and I joined NVIDIA 4 years ago, and I work on scientific applications. The last few years at NVIDIA, I've been working on Gromacs primarily, so that's what I'm going to be talking about today. So this work is done in, just going to check that, yeah, hopefully you can see that okay. This work is done in collaboration with the Gromacs core developers. So for more information on who they are, I'm sure a lot of you know them, a lot of them already. They're mostly based in Stockholm, but here's their names here from a paper that we co-authored last year. A fairly short time to describe the work here in this talk today, but for anyone that's interested in more details, I refer you both to this paper and also to this NVIDIA blog that I wrote last year as well, this blog article is quite closely aligned with the material that I'm going to be talking about in this talk, although obviously I'll be giving some updates from then. Okay, so I'm just going to see if I can, I've got a banner across the top here, see if I can remove it. I'm not sure how to hide that. I don't know if that's obscuring the view for you guys as well, or just for me, but anyway, I'll go ahead.
No, it's looking fine, Alan.
It's looking okay, okay, yeah. Right, that's fine. So, yeah, as I guess most people will be familiar with Gromacs from this consortium, but Gromacs is a molecular dynamics code that evolves systems of particles using the Newtonian equation of motion. And as part of this process, we need to calculate forces between all the particles. So each simulation has many, many particles, and each of them interact with one another and move around based on their interaction. So we need to calculate the forces that the particles exert on each other, and then we need to evolve the positions of the particles based on those forces, and then we need to repeat that many, many, many times. So there's two types of forces, or two main classes of forces. We have the short-range forces. As we know, the magnitude of the forces decreases with distance. So the forces between particles that are closer together are of a higher magnitude than those that are further apart. And that means that for all particles within a certain distance of each other, we need to calculate the forces directly. We're calling these the short-range forces. But we also need to, take into account all the long-range forces as well. But because these are weaker, we can use this trick called particle mesh Ewald, which essentially uses a Fourier transform to allow the calculations to be performed in Fourier space rather than real space, which is a much cheaper computationally. So these forces, before we started this work, these forces were actually all GPU accelerated. Anyway, in fact, Gromacs was one of the first codes, near the start of general purpose programming on GPUs. Gromacs was one of the first codes to take advantage of GPUs. And that's because at that time, when Gromacs was running on CPUs, the vast majority of time was spent in a specific type of short-range force, the most dominant type of short-range force, which is the non-bonded forces. And these were so dominant in the CPU code that, it was possible just to accelerate that part of the code on its own. And it received a large speed up from doing that, from moving it to GPUs. And then therefore the whole application, as a result of that, just moving that one part of the code, received a big speed up. But as years have gone past, the GPUs have become faster and faster, such that this part of the code has been accelerated away so far now that all the other parts of the code have become important. And we got to a point where, we weren't getting, full advantage from each new GPU generation because all the non-accelerated parts had become significant to performance. And that includes not just computation, but also communication between multiple GPUs when we want to use multiple GPUs for the same simulation. So we've been addressing that over the last few years, and we've now got to a stage where the performance is much, much better than it was. So I'm going to use some cartoons to illustrate that. So this gives you it's an illustration of a single time step. So as I say, Gromacs will run, evolve over many time steps, and each one of them will look something like this. Of course, I've vastly simplified things here, but this gives you a rough idea. So this is previously, before the work that I'm going to talk about in this, the work I'm talking about here. In particular, this is if you're using Gromacs 2019 or earlier, then what will happen is you will be able to accelerate, you'll be able to offload the short range forces and the PME forces to the GPU. And these are in green here, indicating that they're running on the GPU. But the rest of the time step had to run on the CPU, the main parts being what we call the update and constraints, which is the part of the time step where the positions are updated based on the forces and some constraints are applied. And then some internal buffer operations, which do transform different data layouts and do reductions. These had to be performed on the CPU. And so that's indicated in blue here. As I mentioned, because they're running on the CPU, they're not able to take advantage of GPU acceleration, and therefore they're relatively slow. And not just that, it means that because part of the time step is on the GPU and part is on the CPU, then it requires the movement of data between these two devices, over and over again every time step. So the D to H means device to host. Means after the GPU kernel is complete, we have to copy data back to the CPU to do these CPU operations. And then similarly, before each GPU operation, we have to copy the data host to device to the GPU. And these data transfers are slow as well. They're in red to indicate they're going over the PCI bus, which is the interconnect that connects the CPU and the GPU together. And by the way, if you're running on a very old version of Gromacs before 2018, then you won't even be able to take advantage of PME on GPU. This would be running, this would be blue as well, and it would be huge. It would be very, very slow. This just echoes Paul's point that please make sure you update. If you're running an old version of Gromacs, please, the most important thing is to update to as new version as possible, because the differences can be huge in performance by taking advantage of the more recent offloading capabilities to the GPU. Okay, so this was previously, I say, Gromacs 2019. So we did a lot of optimizations for Gromacs 2020, which was the version that was released at the start of last year. And these involved offloading everything to the GPU. So you can see here that everything is now green. And that is that, in particular, we offloaded the update and constraints part of the time step and the buffer ops and some other things that are not mentioned here. And these have been accelerated. They're much quicker by themselves, but also we don't need these red parts. There's no red anymore, which means there's no data transfers required because the data can just stay on the GPU memory. It doesn't have to be transferred back and forward from CPU to GPU over and over again. And this has quite a substantial effect on performance. So that's the situation for single GPU. But we've also done a lot of work on multi-GPU optimizations. So this is getting a bit more complex, but let me describe what I'm showing here. So here I'm showing a simulation with 4 GPUs running in tandem. So Gromacs, when it splits its activities up into multiple GPUs, it has 2 main levels of doing this. The very top has this task level parallelism where it assigns different tasks to it can assign different tasks to different GPUs, or in particular, it can assign the PME, so the long range forces, to its own GPU. So it can use one of the GPUs in the simulation to calculate the PME, the long range forces, and it can use the remaining GPUs in the simulation to calculate what we call PP, particle, or what this does is the short range forces plus all the other stuff like the updating constraints. And the PPE can be decomposed across, itself can be decomposed across multiple GPUs. I'm showing it decomposed across 3 here. But at the moment, and I'll come back to this later, at the moment the PME can't be decomposed across multiple GPUs. It's just got a single GPU and it operates, as I say, in tandem with these multiple PP GPUs. So previously in Gromacs 2019 and earlier, this would look like this, where we can offload the force calculations, the greens, to the GPU, but all the rest of the stuff, similar to I mentioned for the single GPU case, everything is on the CPU all the rest of the time step. And we have not only these data transfers between the CPU and GPU in red, but we also have these things shown in arrows, which is the required data movements between these distinct GPUs, or the distinct MPI tasks. So we're using MPI here to control the GPUs, and we have these data transfers between these MPI tasks in order, if we're running the same simulation across multiple GPUs, then the different parts of that simulation need to talk to each other, and they need to exchange data, both with it, between the PP tasks and also between the PP and PME tasks. And the combination of these things meant that, previous to this work, this picture here was very, very slow. There was a huge amount of overhead associated with all this data movement and these CPU resident computations, that actually, in most cases, it wasn't really worth trying to run on multiple GPUs. Anyone that tried to do that would actually often find that the performance went down rather than up over a single GPU. So this is the new situation where the same philosophy that we need to offload everything to the GPU on each time step so that we can just keep the data resident on each GPU. We don't have to have data going back and forward between the CPU and GPU. And also all the computation is now done on the GPU, so that's fast as well. So everything is green here. But the complication here is that, of course, we still need these data transfers to do a single simulation across multiple GPUs. They need to talk to each other. They need to exchange data with each other regularly every time step. And the way we've implemented that is via these what we call P2P, peer-to-peer transfers that allow data movement to occur directly between the GPU memory spaces. So the difference is that we've completely taken the CPU out of the equation here. It's not used for these. The data transfers are just done directly from a memory space on one GPU to the memory space on the other GPU. And for servers that have high bandwidth connections between the GPUs, then this gives very fast performance. It also gives, even for servers that don't have high bandwidth connections, it gives much better performance than the previous version because it's a lot more asynchronous. Things can happen without having to involve the CPU and synchronize with the CPU. So I'll show you. Okay, so this slide just gives a bit more details about how we did that for one of the types of communications, but I won't go into the details on this. In the interest of time, the blog article has more details on this, so please have a look at that if you're interested. But what I'll do now is jump to showing some results from doing this work. So what I'll show is results from 3 different system sizes, systems that range in size. We've chosen these to what we think is typically representative of the range of sizes that that researchers typically look at or typically use, ranging from around 100,000 atoms up to 1 million atoms. Of course, if anyone thinks that we've got that wrong, this range of sizes, then we'd be very interested to hear that. We want to try and reflect our studies and our work based on what people are actually doing. So this graph shows the effect of the optimizations that I've described. The graph is taken from this blog, and as such, it was I created this about a year ago, so it's on our previous generation hardware, which is V100, the Volta generation. The next graph will show you the update to the new generation. But what this graph is comparing, it's comparing the old version of Gromacs before these optimizations. That's the 2019 version with the new version, the version where these came in, which was last year's 2020 version. And what I'm showing is results using 4 GPUs for each simulation. So this is 4, each of these has 4 V100 GPUs. And I've set the results to 1 for the previous version. So the 2020 results show the speed up that we're getting with these optimizations switched on essentially. So we can see the benefit that we get ranges with the system size, and it's, we're getting more benefit for the larger size, but we're still within a factor of 2 to a factor of 3 benefit we get from these optimizations. So this really shows you that you can have a really large effect by using the latest version of Gromacs with these optimizations enabled, and I'll come back to show you how to enable these. So this graph updates the previous results. It's the same test cases, but now showing it on our latest GPUs, A100. I'm also showing it with the latest version of Gromacs 2021, which was just released a few weeks ago. Gromacs 21 has a few minor optimizations over 2020, but nothing as dramatic as what we saw going from 19 to 20. But you should definitely update to 21 because it has better stability, etc. as well. So I urge everyone to get this new version. There's actually a 2021.1 version that was just released, I think, yesterday. So I'll go for that. So I'm also including this graph, the comparison to CPU. So I'm setting here as the baseline the results using 2 CPUs. So these are best-in-class CPUs, the AMD EPYC 7742 CPUs. Each of these has 64 cores. So, so I'm using 2 of these as a baseline, and that's 128 cores. So these are the same CPUs that are in the Archer 2 machine in the UK. So that's essentially comparing to using a single node of Archer, which has 2 CPUs in it. And I'm listing results for 1, 2, and 4 GPUs for each of these cases. And we can see that we're able to, especially for the larger cases, and it's not really surprising. Go to the larger cases, we're able to take advantage of more GPUs in a more straightforward way. We're able to get decent scaling up to the 4 GPUs, and we're seeing up to a factor of 6 benefit over these two AMD ROM CPUs when we use 4 A100 GPUs for these larger cases. We're still getting good benefits for the smaller cases, but the benefit of using multi-GPU does decrease. What I would say is that whether you want to use the multi-GPU configuration or not really depends on whether you're more interested in time to solution. You want the fastest time to solution for any particular simulation, or if instead you're actually more interested in throughput, you've got many simulations to run and you just want the best throughput for them, then usually the best thing to do is just to run a single simulation per GPU, and then run multiple simulations across the multiple GPUs. Actually, what I found is you can actually run you can actually get even more benefit from running multiple simulations per GPU. If you're just interested in throughput, you can use something. NVIDIA has a service called Multiprocess Service MPS. It's just a single line to switch it on, and your script, and it allows multiple jobs to run on the same GPU in parallel with each other. If anyone's interested in exploring that, then please just get in touch with me. I can help you get that set up. Okay, so anyone that's used Gromacs will probably be aware that it can be quite difficult to know what options to use, and there's a vast landscape of different options available. It's quite hard to know which to use to get best performance, this is something that we'd hope to improve in the future, but it still is an issue that it can be difficult to know which to use. So what I've done is in this blog, I've included a how-to section. I've included an enabling optimizations for your simulation section, which gives you the explicit commands that I use to generate these results, to allow you to copy those. But it does, at the moment, it does require a few things. It requires you to build with, so Gromacs has its own built-in MPI library. So it's basically, if you don't provide an external MPI library, then this is what Gromacs will use by default. And this is required actually to enable these optimizations at the moment. I'll come back to that. So you need to build Gromacs with its thread MPI, its internal MPI library. That means that these optimizations are limited to a single compute node. It means that you can't trigger the communication optimizations can't be triggered across multiple nodes because that will require an external MPI library. And we are working on that. I'll come back to that. It also requires a correct combination of environment variables and MD-run options, as described in the blog. And if you want to have these, if you're running on multiple GPUs and you want to have all these optimizations enabled, including the combination of GPU communications and the GPU update and constraints, then you need to use HBonds. Your simulation has to have update groups enabled, which is done automatically, or usually done automatically when you set the constraints to be HBonds constraints rather than all bonds constraints in your MDP file when you're creating your TPR. So again, there's more information in the blog on this. So yeah, we will aim to improve both the automation and removal of the limitations in future releases of Gromacs. In particular, as I mentioned, that the work I've described so far, if you're using the release version of Gromacs, then they're limited. They require you to build Gromacs with thread MPI, which means it can only be used within a single compute node. But we now have codes to remove that limitation. We can now trigger these optimizations if you build Gromacs with an external MPI library, as long as that MPI library is CUDA aware. And most, like for example, if you use OpenMPI, a modern version of OpenMPI, that will be CUDA aware. CUDA aware means that the MPI library understands that GPU memory spaces, so it can have MPI communications operating directly in the GPU memory. Everything is open, so anyone that wanted to try that can have a look at. So we have the ongoing work to merge this into the main branch of Gromacs at the moment, and that includes the branch that this is available. And so anyone, if they want to try that, they can. So this will remove the limitation on single node, but as I mentioned earlier, at the moment with Gromacs, with the release version, if we want to have multiple GPUs, then we can only have a single GPU operating on the PME long-range forces. And what happens therefore is as you try and scale up, you always get to a point where that single PME GPU becomes the limiting factor, and it's not possible to, to scale past that. So what we need is PME decomposition on the GPU, the same way as you can decompose on this for the CPU version to scale out to many compute nodes. And again, we have a prototype version for that at the moment. And yeah, once we have this CUDA-aware branch merge, we'll start working on merging the version with PME GPU decomposition. But just to give you a preview of results for that. So this is looking at the larger STMV case, the 1 million atom case, and looking at the performance as we scale out the number of GPUs. So we're running on servers that have 4 GPUs per node, running up to 4 nodes here. Let's just look at the black results, the red results of the previous filter, but the black ones are the new Ampere. So if we run, with the open circles show the code before we did any of the optimizations described in this work. And you can see the performance is very limited there. If we switch on the optimizations described earlier in the blog, then we have the black squares. So we see we get better performance and also better scaling, but we hit this limit when we get to 2 nodes, 8 GPUs, where we really can't scale past that because of that single PME GPU. But when we move to the PME decomposition, which is the dotted line in black triangles, then we get past that limitation and we're able to decompose that PME as well as the other parts of the calculation and continue to scale this up to, we're getting above the 100 nanoseconds per day for this, so we go up to 16 GPUs, which is 4 compute nodes. Yeah, this is, the performance will depend. I mean, obviously the scaling performance is going to be better for larger system sizes. Again, for smaller system sizes, you won't see such good multi-node scaling. But again, my feeling is that most people are probably interested in running a large batch of simulations. So the best configuration there is to run each simulation within a node and then run across many nodes to get your ensemble completed. Okay, so that's me finished. Quick summary. Modern GPUs have become so fast in performing the Gromacs force calculations that all the other parts of the calculation became the bottleneck. So we had to work on that and accelerate all those other parts of Timestep, including the communications. And we've been doing that over the last few years with the core Gromacs developers, and we've got large improvements from that. These are all in place in the release versions of Gromacs, and what we've been working on more recently is improving multi-node performance and scaling, including this PME GPU decomposition, and this is a work in progress to get that into the release versions. And we have a bunch of other improvements that we're working on at the moment as well to continue to improve the code.